So, you want to build an electric race car. That's cool. We will be needing a powertrain, the part of the car that makes it go. How do you build a powertrain? I'm glad you asked. Hi, I'm Caleb Mitchell, Powertrain Subsystem Lead at Liberty Motorsports. As a first-year team, we spent a lot of time doing research. And everything we learned was common engineering knowledge, but it took forever to learn everything we had to do to build a car. I'm proud to present this consolidated course, an Engineering Powertrain 101, that will teach you everything that we had to learn during our first year. Everything from the general, how do you set goals, to how do you tune a differential, or what is the exact equation I need to size an O-ring to fit into my motor. Of course, this is all general stuff. Your specific car might require a little more research. Provided in the video description is a table of contents where you can skip to whatever information you want, or you could watch the whole class together. If this is your first year with Liberty Motorsports Powertrain team, welcome, and I recommend you watch the whole thing from beginning to end. Everything I say here can also be found online so that you can verify that I'm teaching you the right stuff. Chapter 1, Getting Ready for the Season. If this is your first time on a formula team, it can be really daunting. You need to learn everything from what is a differential to, what do I have to do to make my car win? It can be really challenging, and that's why it's important to set goals. We want to begin by keeping our solution space large. It's the beginning of the season, so no bets are off. We want to start by making large, broad, general goals, and then getting more and more and more specific over time by setting good goals before the season and then during the season. Obviously, winning the race is everyone's goal, but that goal will not help you narrow down your design choices. Instead, if you're a first-year team, try something a little bit more specific yet achievable. Like, we want a car that will not break during any of the competition, and then base all of your design decisions off of that. Or we just want to pass technical inspection, because very few first-year teams in the electric vehicle competition apparently do. If you're a second or later year team, you might have more specific performance-based goals, like we want to shave a couple of seconds off of our 0 to 60 time by improving our power-to-weight ratio. Race car design involves a lot of trade-off. Obviously, heavier cars are slower, but they're going to be more durable. Or more rigid cars might end up being heavier, but you have better energy transfer among the components. So we need a way to visualize our goals clearly and figure out what trade-off we're going to do. We found a really helpful tool to deal with this. Make a sliding scale with every trade-off you can think of on the race car. For example, weight versus rigidity. And figure out where on the scale you want to be. So if you want your car to be very reliable, then you might put the scale here. If you're willing to sacrifice reliability for a little bit of extra speed, then maybe move it over. Not necessarily recommended. And then throughout the season, base your design decisions off of where you want it to be on that scale. Obviously, you don't want your car to be heavy as a tank, but you definitely don't want your car to be falling apart just because it's very, very light and quick. I think our team had about 10 major trade-offs that we could think of. You've set some good goals now, but it isn't necessarily time to start making design decisions yet. The next most important thing, or perhaps even the most important thing that you can do, is read the rules for the competition. Again, what we've heard from judges is that a surprising number of teams fail because of very small little rules that you completely miss. That happened a few times even within our own subsystem, that we'd be making a design and then someone would point out some rules somewhere else in the rule book that we hadn't even thought to look, and we'd have to make it change the design. So our subsystem became very familiar with the rules, and the way that I recommend conducting that is we had every single team member make a spreadsheet that was a summary of the rules. So like rule number in one column, summary of what that rule means in another column. Go through the entire rule book and find that for every rule that could have anything to do with the powertrain. Every team member does that, then you compare notes and see if anyone's missing anything. Now you successfully not only read the rules, but read them in a thorough way that will help you remember them, and if you missed anything, another subsystem member would have caught that. We also made a few quizzes just on an online free quiz maker that allowed us to test one another on the rules to make sure that we knew them really, really well. Because you could build the best car in the world, but if you don't pass inspection, then you're not going to be racing it. Before I move on, there are a few more general principles that I want to go over for powertrain design. Things you should know. One is keep it simple, stupid. Just make sure that you do that, because there were a lot of things that we found we made a little too complicated, and I might go over some of those. And we wish that we had done it simply, because that's cheaper and more reliable. The other principle that you should know with powertrain is rotational inertia will slow the car down. If you're in a more advanced engineering courses, obviously you know that by heart, but if you're a freshman, then it might not be as obvious that rotational mass will always slow the car down, so just keep that in mind. I didn't know if everyone would be familiar with some of the basic parts of a powertrain, just to know the words I'm saying. So this is the anatomy of a powertrain in a nutshell. You start off with the motor, or if it was a combustion engine, just a regular engine. And that takes the stored chemical or electrical power and converts it to mechanical power. And our goal of our whole powertrain is just take that motor power and to send it to the wheels. So right after the motor you have a transmission, and the transmission, just as said in the name, transmits that power from the motor to the rest of the drivetrain. And a lot of times it'll have a changing gear ratio as well. So maybe the motor outputs a certain amount of torque and you want to have more torque but less speed, then you could use gearing to do that. The picture on the top shows a more complex automatic transmission of just a standard gas-powered vehicle, and then below that is a much simpler transmission, but it still transmits power nonetheless, of just a simple one sprocket to another. The differential, if you don't know what that is, we'll get into more details, but think about it as it splits the power from the transmission to both axles. And then we just go from the axles right to the wheels. So all together it looks like this. You've got your four wheels here, and then the parts can be rearranged depending on like which wheels you're powering, how many motors you've got. But in general, you'll see this kind of thing of the motor transmitting the power to the wheels through the transmission, a differential, and an axle. Not all of those components are necessary. I've seen ones that look like this, where you still got a motor, you still got a transmission in the form of a little gearbox, and then that just goes directly into the wheels. So it can vary, but in general you've got those same basic components. Now that you've set goals and know the rules, it's time for Chapter 2. Chapter 2. General Vehicle Layouts. There are multiple levels of design. You got to choose the overall layout for your vehicle, you got to do sub-assembly design, you got to do even secondary level sub-assembly design, part design, and choosing specific components, your nuts, your bolts, your O-rings, your washers, everything. The first three items you want to decide on are these: your tires, your motor, and the overall layout of your components. So you're going to be rear-wheel drive, front-wheel drive, etc. Let's talk about the overall layout. There are several that I'm familiar with, and I'll go over those. There may be more out there. It's up to your team, obviously, to do the research in depth and decide what one is best for your approach, based off of your goals. Rear-wheel drive cars are simple, space-efficient, and don't weigh a lot. All-wheel drive cars have a little bit more traction for accelerating, braking, and turning. I've never seen a team use front-wheel drive. If you're doing rear-wheel drive, you can have either one motor or two. Obviously, having two motors will give you a little bit more power. There are some power restrictions in the FSAE rules, though, so be aware of that. And they are heavier and a little bit more complex. But depending on your power goals, maybe that is what you want to do. Single motor systems may be a little bit less powerful, but they are simpler as well. This is the layout that we ultimately went with. If you decide to go with this layout, make sure you don't do it because that's what everybody does. Make sure that you have a good reason for doing it that your team can defend to the judges. If you do an all-wheel drive system, or even if you don't, you have to choose whether you want a motor that is built into the hub of the wheel or that is inside of your chassis. Now, having a motor in the hub of the wheel is interesting. It means that you don't need axles and shafts or pretty much any traditional components. Instead, you just go right from your motor to a planetary gear directly into the wheel. So it's a very compact system. However, I don't know how challenging it is to build. We haven't attempted it yet. Might be something to consider in the future. But they have more mass than that is not a part of the sprung body. Obviously, you want as much of the mass as possible to be inside of the part of your car that is like on the springs. That way you can control dynamically what's happening in the vehicle a little bit more. However, I do know of actual Formula Electric teams that use this approach, so it's completely valid. Just make sure that you know how to do it right. Alternatively, again, you can have the motors both on the inside of the chassis. Let's talk about the other two parts of overall design that will guide the design of the rest of your vehicle, which are the motor choice and the tire choice. On our team, the tires were chosen by suspension, but they had to talk with us about what they were doing because the tire diameter affects the obviously the top speed of your vehicle, as well as the rotational mass will affect the acceleration rate of the car. Basically, it affects the gear ratio overall. And then the traction will affect like your braking and your acceleration, your grip around turns, etc. That's a little bit more advanced math. As a first year, you might not be doing that level of calculations. That'll be up to you. But if you are doing more advanced calculations on your vehicle dynamics around turns and your differential, etc., then that tire grip data will be huge on your powertrain as well. Otherwise, the tire grip more so affects suspension team, which is why they're the ones that ultimately choose a tire compound, diameter, wall thickness, etc. On our team also, the electrical subsystem was the one that chose our motor. I do know teams where the powertrain chooses it, so you'll have to decide what's best for you guys. We like doing it our way because as long as the electrical team knew what the output torque requirements were for the vehicle to work well, powertrain could use whatever gearing we needed to get the performance out of the motor that we wanted. And the other requirements, power, amperage, voltage, etc., cooling, that all affects the electrical team more than it affects the powertrain. On our team, aerodynamics was also in charge of our cooling lines. Of course, we helped route those as well. And did some of the calculations for them too, but mostly because aerodynamics had our fluids experts in the first place, that's why we had them doing that.
I would like to teach you how to derive your vehicle's state equations next, but there's a lot of detail on those equations, and I thought it'd be best to upload it separately in case I need to make adjustments. So I'll put a link to the math video at the beginning of the YouTube description. If you want to watch in the order I intend, go ahead and view that one before coming back to this. From now on, we will break down each component one at a time, and I'll teach you as much as I can remember about designing that part. Select your components after deriving your state equations because equations depend on the efficiency of your chosen components. So there's an iterative process of trying new components, plugging them into the equations, and fine-tuning your selection to meet your goals. Chapter 3. A few tips regarding your motor. Motors have two parts, a rotor, which is the turning part, and a stator, which remains stationary. Usually the stator is on the outside of the motor, so you can easily bolt it to a rigid body, while the visible part of the rotor is merely a shaft that protrudes from the stator. I cannot advise you what motor to get because it depends so much on your team's preferences, but I can advise you about the motors similar to the ones we chose, the Emrax 228. This motor is very common in FSAE because of its power, torque, and speed ratings. If you buy this motor new from Emrax, give yourselves at least 6 months for it to arrive since it ships from Europe. I would not recommend purchasing the dog bone shaped mounting plate since I'm sure you can make your own mount that is light, rigid, and designed perfectly for your car. The Emrax 228 is a very weird motor because of how it moves. As you can see by watching this YouTube video of Team Swinburne's motor test, the rotor is external. In other words, the green highlighted portion here all rotates while the red plate in the back remains stationary. This means you need a thin scatter shield around the whole circumference of the motor. Specifications for that are in the FSAE rules. The wires and coolant lines go into the stator in the back, which is also the only part of the motor that bolts direct to the car's frame. Here's how you mount your motor. 1. Take the motor and bolt the stator directly to a sturdy mount. 2. Make sure your motor has a shaft connected to the rotor, pointed opposite from the stator. 3. Add a properly sized bearing to that shaft. 4. That bearing will be mounted into another rigid support. So now you have the motor supported neatly from both ends. These supports can be comparatively lightweight since they share the load. We'll talk more about gearing in a moment, but let's assume for now that you have a single motorcycle sprocket attached to your motor. Emrax lets you customize your drive shaft upon ordering. You can either mount that shaft to the front like this so it spins the whole rotor, or you can have it protruding through the hole in the back of your stator. This means you'll need a hole in the middle of your mounting plate, but you'll need that for coolant and wires and sensors anyway, so it's not a problem. But there are other problems with bringing the shaft through this side of the stator. First, there's extra complexity because you need 2 shafts. One to support the motor on the right, another holding the sprocket on the left. We chose this approach because we thought it could make the stator mounts strong enough to hold everything from one side, so we could remove the opposing supports and simplify the design. We were wrong. Unless we made the plate weigh dozens of pounds, it was not going to hold without flexing or worse. It is very important your design is stiff so you don't lose energy to the flexing metal, so we ended up needing opposing supports after all, at which point you might as well just mount the sprocket to that side. Secondly, the encoder is a sensor that measures rotation. It is very useful and is supposed to mount to the back of the motor, right where we put our shaft. This means we had to relocate the encoder from its intended position, which is a huge pain since the encoder requires precise tolerances. Thirdly, look at how close our high-speed sprocket and chain are to the high voltage and cooling lines. If the chain were to break, it could permanently destroy the car and potentially hurt someone. We totally mitigated this risk by overbuilding the chain scatter shield by a lot, manufacturing the shield precisely so it fit between the chain and the fragile components, and adding up to 10 times more insulation to the wires than necessary. We made it even more safe than what you see in this picture, but we could have done it just as safe for a lot cheaper if the sprocket was on the other side of the motor. These are all reasons to make sure that whatever motor you use, the axle goes away from your wires and cooling. Speaking of cooling, you have a choice between straight and right-angled coolant fittings. If it is possible, which it should be provided you front mount the shaft, use straight fittings so you can easily mount and detach the motor without needing to remove the elbow-shaped pieces every time they go through the frame's bolt holes. You need to keep in mind the shape of the shaft as well. Emrax default shaft is not the same shape as any standard motorcycle splines, which means you'll need either a custom sprocket to fit the shaft or a custom shaft to match the sprocket. We made a custom sprocket because we thought it would save time, but it was expensive and that part is now irreplaceable if it gets damaged. I would recommend making a custom shaft. Now, this may not be the case with a front mounting shaft, but with the rear mounted configuration, the shaft was built into the motor, which means you would need to make the shaft in advance, design it precisely to fit Emrax specifications, then send the shaft overseas to Emrax and they will double check the shaft meets desired tolerances before building it into your motor permanently. So, if you want a custom shaft that will make adding off-the-shelf sprockets easy, as I recommend, either find a way to bolt it directly to the motor after the fact, or design and manufacture it well in advance, send it to Emrax, and have them build it into your motor. Chapter 4. Transmissions. Now we're going to talk about transmissions. Why do you need a transmission? Well, a car's motor or engine only provides a certain range of speeds and torques. If you need different torque or RPMs at the wheels than what your motor provides, you can use a transmission to transform the output of the motor to your desired output. If you have multiple gears that shift like a car, you can achieve a whole range of outputs compared to the fairly limited input. We will start by overviewing the most common types of transmissions that exist. Then I will go into further detail about chain and sprocket setups, including how to choose the right size and material sprockets, how to estimate forces, how to pick your chain number, how to apply forces to a simulation, and how to model the sprockets in CAD. There are a variety of transmission styles to choose from. A direct drive means you have no transmission. Your motor goes directly into the wheels. This design is simple, but only works if your motor provides the exact output you need, which is unlikely. It also has less parts that can break between your motor and wheels, which is a blessing and a curse. A fixed gear ratio means you have just one consistent set of gears. You cannot shift to other gears while driving. You can accomplish this with two meshed gears as seen on the left, a gear train as seen on the right, or a chain or belt like in the middle. The bottom right corner shows a planetary gear set, in which several planetary gears revolve around a sun gear to make it turn. A manual transmission allows a driver to manually vary the gear ratio while driving. This is useful if you need a wide range of torques and wheel speeds to get the performance out of your car that you want. To the upper left is a traditional manual transmission for a stick-shift car. It uses a part called a clutch to engage and disengage the engine from the gears as the driver switches which gears are being used. Top right photo is a bicycle cassette. Bottom left is a forward-reverse gearbox which has just one fixed gear ratio, but by changing gears, you switch the direction of the wheels without changing motor direction. Finally, planetary gears can be used as a manual transmission by changing which portion, the ring gear, planetary gears, or sun gear, you hold in place. Multiple planetary gears in series can give you even more options. Such transmissions are sold commercially in multiple sizes. In an automatic transmission, the gears are shifted by a computer called a transmission control unit. The one on the left is like what you might find in your car. The one on the right is called a continuously variable transmission. This is a very smooth type of transmission because it makes continuous adjustments instead of shifting between discrete gears, but critics call it inefficient because of belt slippage and stretch. I can't tell you what style is best for you, but I can say what we chose and why. Now, most races do not allow driving in reverse, so there was no need to use any transmission with a reverse gear. If we wanted to drive backwards during testing, we could just reverse the motor itself. Shifting gears is usually unnecessary for electric vehicles. Even Tesla doesn't have a standard transmission. This is because electric motors already have the perfect torque curve for accelerating a car. At 0 RPMs, they have max torque so you can accelerate quickly. Then, when you pick up speed, torque decreases, but you don't really need high torque at that point because the car is already moving quickly. So, all you need is a fixed, optimized gear ratio. Again, we considered all options. Our motor being inside the chassis made planetary gears kind of impractical, and spur gears are often heavy, so it was belt versus chain. Belts are more slippery and stretchy, chains are heavier and have friction between the links. Inertia and efficiency equations will tell you what's best for you. We chose the chain and sprocket approach. I want you to remain open to all transmissions, but since so many teams use a chain, I will now teach you how to calculate your forces to determine specific component selection. First, I'm going to demonstrate the usefulness of a chain and define some terms. These Legos represent the rear axle of a drivetrain. When the wheel turns, the car goes. Your motor will probably not have the exact output speed and torque that you want for the wheels. Usually it will have a disturbingly high RPMs and very low torque. This is because of the physics of how motors work. We can decrease RPMs to a practical range while increasing torque by adding a transmission. Consider these gears. If I attach the motor to the little gear and the wheels to the bigger gear, we've created a simple transmission. A gear connected to the motor is called the driving gear because it drives the rest of the system forward. The sprocket mounted to the axle is called the driven gear. My driving gear only has 24 teeth. My driven gear has 40. So, when I turn the driving sprocket a full rotation, it only causes the big one to turn 24 teeth out of 40 total teeth. So the big sprocket turns 3/5 of the speed of the little sprocket. This is called the velocity gear ratio, and it is represented in three ways. Number of driving teeth over driven teeth, driving diameter over driven diameter, or driven speed over driving speed. There's also something called the torque gear ratio, and that is the opposite, because when speed increases, torque always decreases. So, our velocity gear ratio is 3/5, while our torque gear ratio is 5/3. If that's hard to remember, just ignore the terms and remember velocity gear ratio is input size over output size, and torque is the opposite of that. So, let's consider some numbers. Suppose our motor supplies 30 Newton meters of torque at 100 RPMs. Our gear ratio being 3/5, we multiply the velocity by 3 over 5 to get 60 RPMs. Then we multiply the torque by 5 over 3 to get 50 Newton meters. You can use the wheel circumference to get the velocity of the race car. You will probably be doing this in reverse though. You know the specs of your motor, you know what output you want, you just need to do the math to figure out the ratio. Combine this with the state equations that take into account losses from external forces, and you can determine a gear ratio that optimizes acceleration and speed. This works the exact same way for sprockets and pulleys. The only difference is gears turn opposite each other. Sprockets with chain don't. Now that you know what a gear ratio is, you can drive your state equations to learn how to optimize it. Now let's talk about component selection. Once you have a ballpark for your gear ratio, you can start shopping for sprockets and chain. Motorcycle sprockets are usually lighter than industrial ones, so I recommend shopping in that market. Motorcycle chains come in sizes of 420, 425, 520, 525, 530, and 630. RB Racing has a good resource for seeing what chain number corresponds with what pitch and sprocket width. Buy the lightest size you can that still reliably handles the forces you need. You can also purchase a chain that has rubber seals for even greater efficiency. No seal, O-ring, and X-ring are the most common, with X-ring supposedly providing the most longevity. Regardless of seal, make sure you lubricate your chain properly per manufacturer's instructions. You can buy racing-specific motorcycle sprockets. The driving sprocket is usually steel, while the driven is aluminum. On many websites, you'll need to tell them what motorcycle the system is for. Try to find a model of motorcycle to input that has similar or greater power to your car. Different motorcycles will have different splines and bolt patterns, so if you make a custom shaft, know what motorcycle spline you're mimicking in advance. You're in even better luck if you can find a model that uses some industrial standard spline. A lot of small engines are measured in cc's, which is the volume in the cylinders in cubic centimeters. You should not try to convert from cc to horsepower, since converting from a volume to power is ridiculous. Try to find a motorcycle power rating specifically. When you buy your sprocket, make sure the aluminum driven one has a tough hard coat on it to prevent wear. The brand Vortex calls this their F5 hard coat. Other brands may have different names. To justify your purchase, you need to calculate the forces experienced by the sprockets in the chain. Let's do that now. Assume the system is at static equilibrium. Torque is being applied to the sprocket, but the system isn't moving. It's like you've got the brakes on. This is a good representation of what happens every time you floor it while stopped. Since there is static equilibrium, Newton's law tells us that the sprocket is being held in place by a reaction force from the chain acting on the sprocket. This force times the sprocket's radius is equal to the torque. The chain applies a force of equal magnitude to the big sprocket, which therefore experiences a large torque where the sprocket meets the rear axle. The chain, meanwhile, is experiencing a tensile force also equal to the yellow reaction forces at the sprocket. This is a very simple representation. The torque is obviously much larger at the driven sprocket thanks to its diameter, so why did I say that one gets the weaker, lighter material? It comes down to the forces experienced at the individual teeth. Consider only the driving sprocket. To keep equilibrium, the moment generated by the motor must be reacted by an opposite moment. Well, that force that causes the reverse moment is not only at one tooth, it is distributed amongst all the teeth that contact the chain. These little forces added together must add up to counteract our torque, and the sum of all those forces equals the tension in the chain. Let's try it with some made-up numbers. Suppose our motor's max torque is 200 Newton meters, and our sprocket has a radius of 20 millimeters. When we divide the supplied torque by the radius, we find the chain is pulling with a force of 10,000 newtons. From the sprocket's perspective, that green force is really all the little yellow forces added up. So take the green force of the chain, divide by the number of teeth pulling on the chain, in this case 6, and you get the reaction force acting on each individual tooth. So even though the chain pulls with 10,000 newtons, each tooth feels under 2,000 newtons. Our other sprocket has a lot more teeth contacting the chain. In this example, 33, which means we divide the 10,000 newton chain force by 33. Each tooth only experiences 303 newtons of force, which is less than a third of the driving teeth. Therefore, we can use a material that is 1/3 the strength of our driving sprocket. This is why steel is necessary for the small sprocket, but aluminum works for the big one. We want the lightest allowable material because less rotational mass means greater acceleration. Now that we know the external forces, we can find the stress in the part to make sure it holds up. All you have to do is make a 3D model of your sprocket and apply SOLIDWORKS simulations, ANSYS, or a similar program. Apply fixtures where the sprocket will react with the shaft, as represented by the red X's, and apply a force to the fewest number of teeth that touch the chain at any given time. or you can hold those teeth fixed and apply a force at the spline. Either works as long as the forces are tangential to the circle's circumference. Run the simulation and you can know what stress your sprocket must overcome. These methods are especially important if you design your own sprocket, but are also good for justifying off-the-shelf choices. You can also look for manufacturer specs. I recommend buying, not designing, sprockets, because if you miscalculated the ideal gear ratio by mistake, you can easily try different sizes by buying new off-the-shelf ones. Keep in mind that your system will experience impulses, sudden forces applied over a fraction of a second, which put even more stress on your components. There are two ways to account for impulses. One is to run dynamic simulations in ANSYS, which I have yet to attempt. I've also heard that as a rule of thumb, you can double the static forces to simulate an impulse, which means you need to buy components that are more than twice as strong as your static analysis would say. If you want to use that rule of thumb, find a source that agrees with it and cite it in your report. This rule of thumb is not the same thing as factor of safety, which must be accounted for separately. You do not want your chain to flop around like this piece here. Instead, you want it tight. There are several kinds of chain tensioners. The most common type is simply a spring-loaded sprocket, or if you used a belt, a spring-loaded pulley, that pushes down on the chain/belt. This is a tried and true design used everywhere from bicycles to cars. Another approach that many teams, including us, have used is to move the sprockets themselves to keep the chain taut. This reduces the number of moving parts and, in our case, improves efficiency while somewhat reducing weight. Most teams choose to move the driven sprocket, not the driving one. We did this with something called an eccentric tensioner. Our axle was mounted to this off-center hole, so when we turned the tensioner, we pulled the axle and the driving sprocket away from the motor, tensioning the chain. We had several holes spaced around the outside of the mounting plate, and which holes you used would determine the placement of the big, non-centered hole. Your chain will stretch over time, so you'll need to move it every so often. This comes with a major drawback. What if the perfect amount of tension lies between two spaces? I recommend using a continuously adjustable approach. You want the option to fine-tune to any position with good precision without locking into specific places. This could be done with a spring or threaded rods which move mounts. This could be used in conjunction with an eccentric tensioner, or it can move the actual differential manifold itself. This is how I would design it. Whatever you do, make sure it is lightweight, rigid, keeps the sprockets aligned, but allows for continuous rather than discrete chain adjustment. For design and simulation purposes, you might want to draw a sprocket with perfectly shaped teeth. The curve of a sprocket tooth is pretty standard, and you can learn how to draw it with Gears Educational Systems PDF. If you're using SolidWorks, I highly recommend utilizing design tables and equations to make a model that automatically generates perfect sprockets when you type the pitch and thickness into an embedded table. If you're a Liberty Motorsports member, I made this easy for you. Find part number X02-0036P-00. If you can't find it, use any of the more recently used Powertrain sprockets and save those. Save the sprocket under a new name. I've set up equations for you in advance to determine the size of the sprocket. So, go to the parts design table, which is an embedded Excel file, and you can enter the pitch, number of teeth, and width of your sprocket. Remember, RB Racing's webpage can tell you what those numbers are for a motorcycle chain number. I also have the data saved somewhere in the table itself. You may need to rebuild your part a few times before the changes show correctly, but the part should automatically generate with the appropriate teeth. All that's left is to add holes, splines, a hub, or other features to your liking. If you want to make your own equation-driven sprocket, watch YouTube videos on how to make design tables if you don't already know how. Then follow the Gears Educational PDF I mentioned before, using your variables and equations instead of typing constants. That way, when you make changes to your table, the model sketch will all scale automatically by following those equations. You see how teeth of a sprocket get narrower at the tip? That's called a bevel, or chamfer depending on who you ask. It helps the chain find the sprocket. You can use this equation to get the correct size of your sweep cut. Obviously H is going to depend on the chain number, but you can still use G equals 0.0625P, or if you like, G equals 0.015625H. The base of your chamfer is usually the base of your tooth, but the motorcycle industry sometimes does things funny for more strength. You can also just get the angle from measuring a sprocket by hand. Chapter 5. Differentials. The differential's purpose is best explained via demonstration. Here I have an axle. We're pretending this is the rear axle of a rear-wheel drive car. I've added the yellow piece as a handhold to represent our big driven sprocket. When I turn it, the wheels roll forward, but look at what happens when I try to go around a bend. Skirt! The wheels didn't roll very well. They practically slid. This is because wheel rolling around the outside of the turn needs to travel a further distance than the inner wheel. It needs to roll just slightly faster than the inner wheel. When we have a straight axle like this, the wheels are forced to move at the same speed as each other. Thus, one is forced to spin around turns. This is the same kind of setup you see in go-karts and drift cars. You might hear it called a welded differential, a spool, or no differential. All of them refer to the same thing, two wheels somehow fixed to one another. If your only racing experience is Mario Kart, you might not think skidding is such a big deal. You fly around the turn and get a shoot out the other side. In reality, that squealing rubber is acting like a brake and you lose tons of momentum. You want your race car to glide through the turn perfectly without burning any rubber. So, you take your axle and add a differential to the middle of it. If you're curious how a differential works, Chevrolet's 1937 video called Around the Corner is the best video on the subject. I've never heard anyone explain it better, and I will not try to top that video by explaining the gearing here. But I can demonstrate to you what is accomplished. When I grab the yellow piece and roll it like before, both wheels get plenty of power, and the car can drive in a straight line. But when I go through a turn, the gearing automatically makes the outside wheel turn as fast as I need relative to the inner one, so we can go around the turn without skidding. Your wheels don't skid, they roll during straights and turns. The most common type of differential is an open or free differential, which is what I've built here. It means the gears are always free to spin and will never lock. This entire assembly is usually enclosed and filled with differential fluid to keep the gears lubricated, but as long as they still spin freely, it is considered an open diff. Open differentials have a big disadvantage when a wheel loses traction. I removed the tread to make this wheel smooth. This represents going over a slick road, mud, or ice. When I turn the differential, it sends all the power to the problematic wheel, making it go faster, while the wheel with perfect traction gets no power. So, your wheel with enough grip isn't turning, while your wheel with no grip turns faster, and you are slowed down. This is because when one wheel turns fast, the differential can't tell whether you are slipping like this or going around a turn. Likewise, if one of your wheels gets stuck, the power will only go to the unstuck wheel, and the other wheel will be unable to break itself free. So, while an open differential is perfect for going around turns and works on a straight if you have grip, you immediately lose efficiency if you go over a slick terrain or hit a bump that lifts one of your wheels. To fix this problem, people have invented all kinds of differentials that remain open around turns but lock during straights. Let me show you what happens when I lock this differential with a Lego piece. See how the wheels cannot turn relative to the differential? Now when I lose grip, yeah, the wheel can still slip, but the other wheel gets power, which means it can push past the slippery bit of road until you get more traction. The next time I go around a turn, the differential unlocks and we can roll smoothly. There are all different kinds of differentials. A limited slip differential, or LSD, is common for race applications. It locks during heavy acceleration. So, if you're just cruising around a turn, the differential will remain open, but if you floor it during a straight, it locks. There are many types of LSDs which have different locking mechanisms. The most common kind uses springs in a clutch pack that is pushed together when the differential sees a lot of force. I'll discuss this more later. A torsion differential accomplishes the same thing as an LSD, but uses fancy worm gear configuration instead of traditional gearing and a clutch. A locking differential is usually computer controlled. When the computer tells it to lock, it locks. When it says to open, it's open. The problem is if your computer locks it at the wrong time, you can end up in a heap of trouble. There are other types of differentials as well, and if you want to know more, Matt Foundry Group has a perfect article for you. I'm assuming after all your research, you might end up with a limited slip differential. They're very common in racing because they can be extremely compact and lightweight and lock during heavy acceleration. It's a very performance-based approach. Within the LSD market, the two brands that I'm aware of Formula students using are Taylor Race Engineering and Drexler Motorsport. You can read the FSAE forums to learn about different teams' experiences with these companies and any other brands I might not be aware of. We chose the Drexler, and since enough other teams use Drexler differentials, I'll go into detail about some things we learned. Firstly, when our Drexler arrived, it had no manual. If your part arrives with no manual, you can contact Drexler for a PDF, but you might need to be persistent. We assumed that the part came with everything necessary, but that was not the case. We were missing a lot of parts that we should have ordered separately. Make sure you have all the following in addition to the main body. 1. Differential fluid. Since we had no manual, we did not know how much or what type of oil. It seems you need about 60 milliliters of Castrol SAF-XJ differential oil. I have suspicions that any 75W140 oil will work fine. According to one of Virginia Tech's Powertrain members, the differential is filled by removing 2 of the 3 screws in the middle of the diff, and then you fill it through one hole until fluid pours out the other. Then you plug the holes. We were also missing 2 needle bearings and 2 rubber axle seals. These go over the axles to keep the axle straight and prevent spilling of differential fluid through the axle holes. We were also missing 2 socket cap screws that hold the axles in place. We did get a big aluminum cylinder with a pre-cut spline. Machine this piece into a useful adapter to mount the driven sprocket and try to remove even more material than we did to reduce weight. Some teams claim they got all the necessary hardware and even tools to assemble it, so I think it depends on who your local distributor is. Most Drexler differentials are adjustable. You can adjust 2 settings, the ramp angle and the preload. Both of these affect how and when the differential locks. Inside the differential are 2 pressure rings. These rings have a diamond-shaped groove between them. A round peg exists inside the groove. When the vehicle accelerates, the peg is jammed forward into the rings, forcing them to separate. When they separate, they push out on a series of clutches, causing the differential to lock up. The angle of the diamond determines how much force is necessary to lock the differential. The smaller the angle, the easier it is for the diff to lock. The whole system is under a spring force too. Changing the spring constant adjusts the preload of the spring, which will also determine whether it is easy or difficult for the differential to lock on top of the ramp angle while you're accelerating. Think of it as a baseline. If the back of the groove has the same angle as the front, the differential will lock under deceleration too. The only time it won't lock is when you're moving at a pretty constant speed, which is usually the condition around turns. This is called a two-way differential because it locks during positive and negative acceleration. If the back of the groove is flat, it will not lock at all during deceleration. This is called a one-way differential. A 1.5-way diff has an angle in the back, but it is less than the acceleration ramp angle, so it does not reverse lock as easily. The Drexler is pretty cool because it has 3 different shaped grooves to choose from. You can disassemble the differential and reassemble it with a different ramp angle. Just make sure you put all the clutches back in the right order. Be very careful about that. You can also adjust the preload by adding a very thin washer or replacing the spring inside the clutch pack, but this is not always necessary. Some differentials have an easy to adjust preload by turning a black external ring. We did not buy this model, but we should have, and we'll do it in the future. If you want to develop some calculations to predict how the ramp angles and preloads will affect performance, you can start with these here equations. Otherwise, a more normal approach is to perform physical tests on different setups to see what improves lap time and handling.
Chapter 6. Axles.
Axles are among the easier parts to choose for their simplicity. In a rear-wheel drive vehicle, you'll have 2 axles, one left and one right. Each axle will be broken into 3 segments with 2 joints. Joint styles include but are not limited to tripod joints, CV joints, U-joints, and all of their subsets. Your job is to build a setup whose spline fits the differential on one end and the wheel hub on the other end. You also need to choose the shaft materials and the joint types that are rigid, lightweight, and have high efficiency. This involves trade-offs, so you need to make your choices based off of good trade-off analysis. Joints become less efficient when they are bent, so try to make it so that when your driver sits in the vehicle, the axles are as straight as possible. Then they can bend when the suspension moves up and down. If you use any form of chain tensioning that involves repositioning the differential, such as eccentric tensioning, it will be impossible to achieve a perfectly straight axle. In that case, just do the best you can. We chose a steel axle from FSAEparts.com for rigidity with 2 tripod joints. The tripod housings went direct into the hub and differential. In the future, I would consider using carbon fiber parts, which will be more expensive but also lighter. Yay. If you want to do this, make sure you research it well. A lot of times, your axle will be oversized, and you'll need to cut it to the appropriate length. Do this at the latest possible time during construction. If your vehicle design changes for unforeseen reasons, you can't really add length back to the axle. Do not forget to buy snap rings to keep the tripod joints in place. You will also need to cut your own grooves for these retaining rings. What lubrication your joints specify depends on what you buy, but any bearing grease will probably work in a pinch. So in summary, rear-wheel drive or otherwise, things to keep in mind are weight, rigidity, joint efficiency, and spline compatibility with other components. Run a few simulations to make sure that your main shaft will support the necessary torque, and then document your results clearly.
Chapter 7. Structural Supports.
Once you have all of your components, you'll want to mount them to your vehicle. Usually the mount shape is determined by the components, but if they just don't fit, the mount design can sometimes influence component design too. My recommendation is to design the mount while the frame team designs the rear frame, that way you can work together. The rigidity of your powertrain mounts will affect your vehicle performance. If your members flex, they're absorbing energy that would otherwise move the car. Therefore, high rigidity and long-term reliability are two important considerations. Since these components don't rotate, extra mass will not harm your acceleration as much as flexibility or damage would. If you're more advanced, the next challenge is to make something that is very light but does not flex. The shape depends on the layout as defined by Chapter 2 and the parts you are specifically mounting to it. Our single motor rear-wheel drive layout means 4 things connected to the manifold: the car's frame, the motor, the differential, and all the scatter shields. The motor is connected via the stator and a single bearing. The scatter shields bolt directly to the rigid structure, and the differential is connected by 2 bearings, or else the bearings are connected to eccentric tensioners that are connected to the frame. Designing the mount can be a long process depending on complexity. First, in your SolidWorks model, position all the components without any mounts. Then, model the mounts to go directly to the parts from the frame. Run thorough and detailed simulations to view the stress accurately. Build up the parts where you need more material. You can also run a type of simulation called topology optimization, which shows you where you can remove unnecessary material. There's a link for a tutorial here. Make changes, simulate, make more changes until the mount morphs into its final ideal form. Remember to account for fatigue to make sure your part is long-lasting. ANSYS is more than capable of fatigue simulations. You can mount each component to the frame separately, or you can mount them all together to a single manifold, then mount that whole manifold to the frame. This is the approach we chose because we wanted to maximize rigidity between the motor and the axle, and figured the best way to do that was to connect them directly. In the end, your frame will be rigid enough that I think several smaller mounts can be just as rigid as one big one. This is especially advantageous because you could put the differential mount on a joint for lightweight swiveling chain tensioning. Our frame team built a fairly large box in which to fit the powertrain however we wanted, but it would be far more ideal to make the box closer to the size of the powertrain so you can mount as directly to the frame as possible. This will keep the design compact, rigid, and light. Some teams, especially those with carbon fiber frames, build the frame such that components mount directly to it. The only advantage to an oversized frame is your frame sub-team can begin construction even if the powertrain team fell behind. The rear suspension also mounts to the rear frame, so the ideal manifold/frame combo would be minimize size while maximizing rigidity and being shaped specially for powertrain and suspension mounting. The powertrain subsystem may need to include then more of the frame in their stress simulations if this approach is used.
Chapter 8. Engineering Fits and O-Rings.
Part 1. Fits. We're going to take a break from discussing specific components to discuss engineering fits. This is because understanding fits is so critical to choosing bearings, which is essentially our last topic. By now I'm sure you figured out that a spline is simply a specially shaped shaft that slides into an identically shaped hole. It is really good for transmitting rotational motion. 2 parts can slide into one another without being splined, however. When this happens, you can have a clearance fit, an interference fit, or a transition fit. For obvious reasons, the part that slides into a hole is called a male, while the part with the hole is called a female. If the male part is smaller than the female, it slides right into the female part without any resistance. This is called a clearance fit. Splined fits often fall into this category. They are good for quick removal. If the male part is larger than the female, deformation of either part must occur for them to squish together. Therefore, a lot of force is required to fit the parts. A silly example of this is putting your arm through a sleeve that's too tight. The shirt will stretch and your arm will be squeezed for it to work. The same thing happens with steel into steel interference fits, but there's a lot more pressure. Our sponsors used an extremely tight press fit to make a titanium sprocket with more complex geometry than typical manufacturing would allow. Press fits usually require special tools, such as this arbor press. A transition fit is right between clearance and interference fits. The parts are almost exactly the same size with very little margin for error. They fit tight enough to stay put, but loose enough that you can slide them apart with hand tools. We used a transition fit where we could not have a part slide around on its own, but it had to be removable by hand tools in a pinch. The tolerance for this was so high, I recommend avoiding it unless absolutely necessary. Within each of the various fit types are several subsets as defined by this table. What you use depends on your needs and manufacturing capabilities. The bases on your right represent various numerical standards for hole tolerances. The exact number that they represent depends on diameter and material. I recommend using a press fit calculator. I've provided one to Liberty Motorsports in Excel, and you can also find ones like this online. If you enter the material properties and diameters of what you're pressing together, you can see how much pressure exists between the parts. How much pressure you want depends on how tightly connected you want your parts and how much pressure your parts can handle before damage. Also take tolerances into account. Your manufacturers can only manufacture parts so precise, and going just a little too high can sometimes add thousands of psi to the fit, while going a little too low can turn a press fit into a straight up loose fit. So to make manufacturing easier, try to find the widest tolerances that will still give you a good range of pressures, and then make sure you include those tolerances on your part drawings. Part 2, O-rings. Most powertrain teams will work with seals. Seals keep fluids in places you want them and out of places you don't. One of the most commonly used types of seals is an O-ring. Sizing these is a common science in the workforce. We needed to size O-rings when the seals in our motor broke and we could not get any replacements from the manufacturer in time, so we had to size them ourselves and order locally. Liberty Motorsports Press Fit Calculator also has an O-ring calculator tab, or you can find O-ring calculators online. Whatever you use, here's what you need to know. O-rings are meant to be deformed. It is by slightly squishing them that you get a good seal. You can have seals that are axial or radial. The slot the O-ring goes into is called a gland. The gland exists in either the male or female pieces. Most of my experience is with radial seals. When the seal is installed in its gland, you want it to stretch so that its new diameter is between 1 and 5% more than its unstretched diameter. And you want it to be squeezed so that its cross-section's width is reduced by 18 to 25%. This should usually give you a sufficient seal. If you stretch it more than 5%, you need to take into account the reduction of cross-sectional area and watch out for snapping. It should look something like this, with fluid unable to escape. Another thing to consider is the durometer of the rubber you choose, which is the scale that tells you how hard or soft the rubber is, with high numbers usually being harder. Don't forget temperature rating too, if you're working on coolant systems. We used this water and chemical resistant high temperature silicone of durometer 70A, which is on the softer side, to make an axial seal for our motor's coolant fittings. The dimensions were chosen using the Excel calculator and then confirmed by Emrax. Chapter 9. Bearings. Now let's talk about bearing sizing, which is engineering speak for buying the right bearing for the job. Now, after reminding myself all that is involved with choosing the best bearings, I realized that I could make an hour-long video on that topic alone. It is best for you to read the bearing catalogs or watch videos from bearing companies instead, but I can show you how to determine the load on a Formula race car and give you some advice that I've noticed other teams tend to overlook. A typical bearing has 3 to 5 parts. The cylinders you can see from the outside are called the races, while inside are the balls or needles depending on bearing type. Sometimes you have a ball cage to space the balls evenly, or a seal to keep the dust out. When buying a bearing, you must consider load ratings, direction of applied loads, RPM ratings, life cycles, bearing grade, maintenance procedures, seals, grease life, type of bearing, and type of fit required to mount the bearing. These are all important factors. Now, these are some, but certainly not all, good bearing manufacturers. They all have online calculators, catalogs, GUIs, or customer support to help you find the right bearing. I particularly recommend SKF's tool for determining the necessary press fit for your bearings, linked here. I'm not partial to SKF, and I recommend browsing for the cheapest option that will meet your needs, even seeking sponsorships. I'll quickly repeat the process I would use if I were to solve for my car's radial bearing forces again. Begin by making a free body diagram, which will look differently for your car. You know the load of the chain and the distance between the parts. Setting the sums of the moments and the forces all equal to 0 gives you the reaction forces at bearings A, B, and C. These are our forces for last year's vehicle. In this example, there are no axial forces, otherwise we'd have to solve for those too. Our motor speed and gear ratio tell us the max RPMs the bearings will experience, and you probably have an idea of shaft diameters, especially for the differential. So together we've got size, speed, and load all known. We just have to find the desirable bearing that is affordable, has low friction, is compatible with our vehicle layout, and is lightweight. There's so much to choose from. Again, I recommend you go straight to the source rather than hearing from me. Depending on the powertrain design, I've seen teams use regular ball bearings, radial bearings, angular contact bearings, self-aligning bearings, and I'm sure even more. Combing through the supplier catalogs will give you a good way to start narrowing down that list. I have just 3 more tips for you before we close. 1. When looking at bearings, you might see bearing standards like these. These standards tell you about the quality of the bearing, how good the internal manufacturing tolerances are. Get the best bearing you can afford within reason, because that will last. We've found ourselves buying bearings that met all of our force and speed specs but were low quality bearings, so while they will not break, I suspect we're needlessly losing efficiency over it. 2. Unless otherwise specified, bearings are designed to press fit into place. So the outer race goes in a female hole, while the inner race is pressed onto a male shaft. This forces the bearing races to squeeze towards the balls, removing wiggle but not crushing them. Overpressing the bearings will damage the balls. Underloading introduces extra play, which will damage the bearing. But pressing to the intended amount improves efficiency and longevity. Whenever you order a bearing, note what type of fit is needed. I recommend finding a more forgiving tolerance fit so that you do not have to spend time and money machining your other parts to fit it perfectly. For the differential, make sure you buy bearings that are already sized for your differential's manufacturing tolerances. That way you can just press fit them on without modifying the diff. If you need to remove the bearing often, find one that is specifically designed for slip fits. The previously mentioned tool by SKF will tell you what range of tolerances are allowed for your bearing. And the bearing catalog should give you that info too. You will need to check the fit for the outer and inner races separately. For example, our deep groove ball bearing specified a press fit for the inner race and a transition fit for the outer one. This transition fit was very hard to machine because it required tolerances of around 4/10,000ths of an inch. I would not recommend doing this ever again. Also keep in mind, depending on the type of press fit, you might not be able to remove your bearings without damaging them once they're on, or you may need to buy a special tool. 3. Suppose you are mounting a shaft with 2 bearings on it, such as your differential or a spool. You want to constrain the part moving side to side, especially if the outer race is experiencing a slip fit. Now you may be tempted to clamp the outer race of each bearing like this, but look at what we just did. I'll exaggerate the reaction forces so you can see we created an axial preload, which can damage the bearing balls. Instead, constrain both sides of one race of one bearing like so. Now, our force pushes against the race instead of the bearing balls. If the inner races of your bearings are slip fits too, or you need to constrain them in any way, also constrain them on either side of the inner race. Never do anything to add unnecessary axial load unless your bearing specifically requires a preload. That extra wear and tear just isn't worth it. Chapter 10. Final advice. I have a few more isolated pieces of advice. Make a safety plan. List everything that can go wrong with your vehicle, and then list how you are going to prevent it and how you are going to react if that thing happens. It'll just help you be prepared, and I imagine will impress any sponsors who ask about safety. 2. Document everything you do very, very well. As you can see, I had almost no photos of my car while making this video just because I didn't take them. Also, I've wanted to access old simulation data and old CAD screenshots way more frequently than I expected, so save every simulation using a clear naming convention and put a description for it. Just take lots and lots of screenshots and photos of your process all along the way. Your simulations will tell you what is most likely to break. Don't forget to check these during testing and practice. Always write down the reasons you made a design decision, even if it seems obvious. You'll be surprised how much about the beginning of the season you forgot when it's report time. Work on the cost report methodically as you design and build. Make good 2D drawings of everything you manufacture as you're doing it. Do not try to bend your powertrain manifold by driving an F-150 over it. Be creative and think outside the box. Clean up after yourself. Do not work by yourself through the night. You won't accomplish much. Be kind to everyone regardless of what they think of you. A happy team is a functional team. If you're a subsystem lead, remember that the more independence and responsibility people feel they've achieved, the better they'll work. Never neglect your team's file management and naming system, even if everyone else abandons it. You will be glad when you can find part numbers 4 months after you thought you would never need them again. If possible, use a project lifecycle management software to check in and check out parts from the cloud. That way 2 people cannot open the same assembly at once. Save backups of everything. Finally, keep the powertrain subsystem fun. Eat donuts, visit Bojangles, and share laughs while working hard. I hope you learned a lot about electric powertrains. We overviewed a lot of basics and touched on some detailed concepts. There's still a lot to learn, but this should give you a reasonable starting place from which to do research and make great design decisions. If you have any questions, you can reach me on LinkedIn or leave a comment and I'll try to respond within the decade. Fan the flames.